Good morning. My name is Ruixiao Sun. I'm a third-year PhD student at the University of South Carolina. Thank you for listening to my presentation. The paper I'm going to present is a joint effort of University of South Carolina, Vanderbilt University, University of Houston, Chattanooga Area Regional Transportation Authority, and the National Renewable Energy Lab. The topic is transit gym, a simulation and evaluation engine for analysis of bus transit systems. Public transit systems face several operational challenges. First, changing ridership patterns requiring optimization of fixed-line services. Second, optimizing vehicle-to-trip assignments to reduce maintenance and operation costs. And third, ensuring equitable and fair coverage to areas with low ridership. State-of-the-art methods formulate these problems as variants of the vehicle routing problem and use data-driven heuristics for optimizing the procedures. However, the evaluation and training of these algorithms require large datasets that provide realistic coverage of various operational uncertainties. A dynamic simulation platform called Transit Gym is presented in this paper. It can bridge this gap by providing the ability to quickly design and execute transit scenarios, focusing on variation of demand models, variations of route networks, and variations of vehicle-to-trip assignments. We need ability to design different demand scenarios and test the algorithms against changing demand and traffic patterns. However, there are several challenges existed. Scenario specification is one of the challenges we are faced. Different transit scenarios, such as different demand models, route networks, and vehicle-to-trip assignments should be designed in our platform so as to provide realistic coverage of various operational uncertainty for testing algorithms. How to specify these scenarios in our platform and allow users to select and execute easily and automatically is the problem we focused on. To handle this problem, first, an integrated, highly scalable cloud backend for various transit scenarios is needed. Second, domain-specific modeling language is used to create domain-specific models based on its representing different scenarios. Another challenge is the calibration of simulation models. For the simulator to remain variable, it is crucial to keep the physical transit network of the city and the simulated transit network in sync. It is common for developers and researchers to retrieve network files from existing platforms such as OpenStreetMap. The data available on these platforms is traditionally crowdsourced, and in many cases, it is not up to date with the actual transportation infrastructure. Therefore, we have performed a stochastic check against the design network and the real traffic data collected from the city, and then fixing any incorrect in the network. This process ensures that the map files are continuously updated, providing an accurate environment for testing and validation. The central contribution of this work is domain-specific language and associated experimentation toolchain and infrastructure to enable subject matter experts to intuitively specify, simulate, and analyze large-scale transit scenarios and their parametric variations. The key contributions are providing, such as a novel domain-specific language that allows intuitive specification and variation of transit scenarios, a methodology to construct and calibrate street maps that conform to real-world transportation infrastructure, a toolchain that automatically configures simulations from the scenarios specified using the domain-specific language, a customized general-purpose simulation for transit scenarios, Of particular significance is an integrated macroscopic energy consumption model that also helps to analyze the energy cost of various transit decisions made by the transportation agency of a city. This paper lies in the intersection of these techniques, model integrated computing, cyber physical systems, wind tunnel, sumo, and energy estimation models. Model integrated computing is a meta modeling technique that puts models at the center of all applications. It allows the creation of domain-specific modeling languages. In the rest of this presentation, I will call it in short as DSML. The DSML describes syntax and the semantics of the models, how models can be constructed, and the constraints that the valid models must satisfy. The DSML tools then interpret models to verify them and generate executables. Cyber physical system wind tunnel is developed by Vanderbilt. It is a model-based heterogeneous simulation, integration, and experimentation framework. This framework has been successfully used in different application domains such as traffic security, high fidelity, dynamical simulation, and smart grid. We are working on extending transit gym using this framework for integrating traffic simulation in Sumo with transportation planning simulation and for large-scale scenario-based experimentation. Sumo is a highly customizable macroscopic transit simulator. It is highly scalable to city-level simulations. We chose Sumo in transit gym because it provides highly detailed capability for modeling transit demand and routes. It is much easier to configure the high fidelity simulations and provides detailed traffic experiment results. Existing energy estimation models for vehicles can be classified as microscopic and macroscopic models according to prediction resolutions. Macroscopic models can only provide energy estimation over a period, thus they are not useful in evaluating energy savings of real-time bus operation strategies. Macroscopic models can estimate energy consumption of vehicle at high frequency levels and are widely adopted in real-time optimal control of traffic involving buses. In a previous study, we have developed machine learning-based macroscopic energy estimation models. This slide presents the framework of our transit gym platform, which utilizes Sumo, DSML, and energy estimation model. The data sources imported in the platform include map, list of vehicle types and parameters, static general transit feed specification named GTFS, and origin destination demand data. The map data can be generated from OpenStreetMaps and converted to road networks in Sumo. The road network contains information such as the number of lanes in street, speed restrictions, and the traffic directions. The list of vehicle types and parameters describe the specification of vehicles that are employed in the city public transit system. The parameters include maximum speed, acceleration and deceleration abilities, passenger capacity, minimum gap between vehicles, and driver preferences. The GTFS data contains the transit route information and the bus stop locations along the route, as well as the trip schedules for a day. The OD demand data contains the details of trips through traffic analysis zone. Each OD matrix cell is associated with a daily time period and describes the representative traffic demand from an origin area zone to a destination area zone. The mentioned data source are input into the following scenario-based simulation. Those input data contain different demand and network scenarios represented as DSML code snippets would then be sent to the interpreter to be processed. The DSML interpreter provides an automatic way for parameter flexibility on vehicle type, scenario generation, vehicle-to-trip mapping, and constraints checker in customizable Sumo simulation. In the progress of scenario-based simulation, three main components are supported: scenario specification, configuration generation, and simulation running. Details of the scenario construction using DSML will be introduced in the next slides. After taking the simulation output values, the energy estimation models are conducted. We are developing algorithms using active learning approaches to address three key problems: hyperparameter selection, model selection, and performance evaluation. Based on these key problems, we have developed artificial neural network-based macroscopic energy estimation model that take 1 Hz vehicle trajectory data as input and output 1 Hz energy consumption estimation. Detailed information of the energy estimation models can be found in our previous work. This slide introduced the DSML we used in our transit gym. This DSML program is separated into the import section and configure section. The first section imports the pre-configured scenario settings that would be used as background data for subsequent code. The import command has 4 variants corresponding to each of the imports. For example, import network configures the map, import vehicle configures the vehicle type, import GTFS configures the GTFS data, and import TD configures transportation demand files. The next section configures one or more simulation based on user input parameters. Here, first, the time range for the simulation will be specified. The schedule command then is used to configure the schedule to be simulated like weekend or weekday. The output sampling period specifies the period for energy summary output. Finally, in the vehicle assignment block, vehicle-to-trip assignments can be defined here. For example, we can simulate a scenario with 1 weekday traffic and 1 weekend traffic in Chattanooga before 12 a.m. and assign a specific vehicle type to all bus routes within block 101. This figure shows parts of the example program that constructs this scenario. This figure presents the detail of how bus mode is implemented in the simulation, demonstrating the interactions between the various components of Sumo. The key steps in the workflow are network refinement, traffic bus stop location retrieving, bus trip generation, vehicle type definition, background daily traffic route generation, person trip generation, and bus and person integrated route generation. The DSML interpreter automate these steps, including calling Sumo packages and writing program to generate Sumo essential input files, as well as other additional settings and arguments are functioned in. The illustration of the results is based on the investigation of Chattanooga, Tennessee, a middle-sized city. The right figure shows the multimodal transit system in Chattanooga operated by Qatar. It contains 16 fixed routes, 3 neighborhood dial-a-ride demand-responsive routes, and a complementary paratransit service. This slide shows the average boarding events per census tract and average ridership per vehicle per route in the investigated Chattanooga region. Our platform can generate various visualization-ready data frames converted from output files, such as edge-based summary, vehicle trajectory, and bus stop information. It provides flexibility for users to select points of interest from these data frames and conduct specific analysis. This paper shows 2 main aspects of the simulation outputs. One is the passenger occupancy status. The other is vehicle trajectory. Some examples of the output analysis visualizations are shown in the following slides. For example, this figure shows the passenger occupancy of each bus along its stop by trips for a whole day. In this slide, the left figure shows the maximum passenger occupancy of each bus along the bus stops by routes. To investigate the occupancy status during different times in a day, the distributions of bus occupancy between different specific hours on specific route can be visualized, showing like this the red figure. The visualization function also can show the summarization of the total boarding and alighting passengers of each bus across a whole day by routes or by trips. See this figure. It can provide users intuitive passengers boarding and alighting status for designing and operating a regional mobility service dynamically. These 2 figures show the distributions of bus speed and average speed of buses on specific routes for several specific hours. It can indicate the traffic conditions during different time periods and traffic mobility on different routes. It can help policy and operation design of the transportation agency of a city. Our platform also offers the ability of investigating energy consumption for different simulation scenarios, such as variation of vehicle trip assignments and variation of demand models. For variation of vehicle trip assignments, an example of comparing energy consumption rate of buses among 3 trip assignment scenarios is shown in this figure. The 3 trip assignment scenarios include base scenario with current data, the scenario using all hybrid buses, and the scenario using all electric buses. From the figure, we can observe that the buses in the scenario using all electric trip assignment generally consumes the least energy than that of using the other assignments across all the routes. For variation of demand models, to check the impacts of background traffic on the energy estimation, 2 scenarios regarding different background demand models are constructed. The first scenario presents the simulation with original daily background traffic, and the second scenario is the simulation with the daily background traffic reduced by 20%. These 2 scenarios are conducted within 1 peak hour simulation. As a simple illustration, the estimated energy consumption rates for 3 bus types under the 2 scenarios are shown like this table. This helps to analyze the energy cost of various transit decisions made by the transportation agency of a city. In sum, we presented the platform Transit Gym. It is an extension of sumo-based transit simulator for simulating a variety of transit scenarios. It provides the ability to rapid design and evaluation of what-if transit scenarios. It's domain-specific modeling language and calibrate cloud sources, street maps and traffic demand patterns for accurate testing and validation. Our experiment results demonstrate the broader feasibility of TransitGym for realistic transit simulation and providing efficient decision support for transportation planning. TransitGym is freely available on GitHub. We are currently working on several extensions to TransitGym, including integrating transportation planning with transit simulation and energy consumption estimation together as a co-simulation using Vanderbilt's cyber-physical systems internal framework. Developing a richer scenario modeling language to incorporate more specific transit use cases. Increasing performance of our simulations through partition traffic simulations, scaling our simulations for broader cloud integration, enhancing visualization of experiment and analysis results. This material is based upon work supported by National Science Foundation under the 3 grants, and we also acknowledge the award from Department of Energy, Office of Energy Efficiency and Renewable Energy. Thank you for your listening. Our project website and GitHub link are attached here.